Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 2, Section 2, Chapter 5, Topic 4, Part 2. Circuit Analysis Techniques for System-Level Analysis.
Circuit analysis techniques play a crucial role in system-level analysis, enabling engineers to cascade components and evaluate system metrics effectively.
Some common circuit analysis techniques used in system-level analysis include 1. Nodal analysis. Nodal analysis involves applying Kirchhoff's current law, KCL, to analyze the voltage distribution and current flow at different nodes in a circuit.
It allows engineers to determine node voltages and currents, which are essential for evaluating circuit performance and analyzing component interactions.
2. Mesh analysis. Mesh analysis applies Kirchhoff's voltage law, KVL, to analyze the voltage drops and current flow in loops or meshes within a circuit.
It provides insights into the voltage and current distribution in different branches of the circuit, facilitating the evaluation of system metrics such as power consumption and signal integrity.
3. Transient analysis. Transient analysis involves simulating the transient behavior of a circuit in response to sudden changes or disturbances, such as switching events or input signals. It allows engineers to assess the dynamic response of the system and evaluate transient effects on system metrics such as signal integrity and timing. 4. Frequency domain analysis. Frequency domain analysis involves analyzing the frequency response of a circuit to sinusoidal input signals across a range of frequencies. It provides insights into circuit performance in the frequency domain, enabling engineers to evaluate system metrics such as frequency response, bandwidth, and filter characteristics. Applications of system-level analysis. System-level analysis has diverse applications across various domains, including 1. Electronic systems design. System-level analysis is used to design and optimize electronic systems, including communication systems, control systems, and power distribution systems. It helps engineers ensure compatibility between different subsystems and achieve desired system performance metrics. 2. Integrated circuit, IC. Design. In IC design, system-level analysis is used to evaluate the behavior of integrated circuits and their interactions with external components and interfaces. It helps validate IC designs, optimize performance, and ensure compliance with design specifications and requirements. 3. Signal integrity analysis. In high-speed digital designs, system-level analysis is employed to assess signal integrity and analyze the impact of interconnects, transmission lines, and routing configurations on signal quality. It helps engineers optimize signal paths, minimize signal distortion, and ensure reliable data transmission in electronic systems. Conclusion. System-level analysis plays a critical role in electronic design, enabling engineers to evaluate the overall performance and behavior of electronic systems. By considering the interactions between various components and subsystems, system-level analysis provides insights into system metrics such as power consumption, signal integrity, timing, and noise. Through the cascading of components and the application of circuit analysis techniques, engineers can analyze system behavior, optimize performance, and ensure compatibility between different subsystems. System-level analysis serves as a valuable tool for validating system designs, identifying design flaws, and optimizing system performance in diverse applications across various domains. Thanks for watching. Please like, share, and subscribe.